All right, everybody. Lecture 9. Let's get started. So just a little bit on housekeeping, because I try and do this, and I'm sure that I haven't had a 100% success rate, but I try and make sure that you're, aware when celebrations are coming. And I mentioned on day 1 that I follow the schedule and syllabus pretty rigorously, so we are continuing to do that, which means that our first celebration is going to be next Friday, not 4 days from now, but next Friday. So we will review on the 7th, and then we will celebrate next Friday. So I just wanted to make sure everybody was aware of that. So we're going to have 2 design examples, one today, one Wednesday. Friday, we're going to do block shear. Then Monday, we're going to do threaded rods. And then it's exam review and celebration. So it's coming up relatively soon. So I just wanted to make sure everybody is aware of that. 2.3 and 2.4 are being graded by the TA. 2.5 is due today. So we're going to have a homework pretty much every day up until the celebration's coming up. Any questions on that? All right. There was a little bit of a discussion before class, and I thought this was worth mentioning. So there was a question about, from a conceptual standpoint, is tensile behavior, tensile capacity, the same thing as axial capacity. And so I think in one of the assignments and whatnot, I might have used the term axial capacity. And that might have been, I don't know, I guess sort of a poor choice of words, at least for the class as a whole. For right now, since the only thing that we're talking about is tensile loads, then right now there's not much difference. But later on, we're going to be looking at members under compression. So basically what we're talking about is if we have an element that's being yanked on and versus an element that's being pushed on like this, both of these elements are experiencing an axial load. Now this one, hold on, I can do better with that one. That one's supposed to be through the middle of it. Both of these are experiencing loads in an axial fashion. In other words, they are along the axis of the member. But the difference is that this one up top, this is tensile, and the bottom one is compressive, okay? So this is tensile, in other words, being yanked on. This is being pushed on. It's compressive. Help if I know how to spell this morning. Now, the reason why we differentiate between the two from a design standpoint is because of how they behave once we start applying load to them. And I think a simple way of putting it is that members in tension tend to want to fracture or yield dependent upon whatever limit state governs. But elements that are in compression like to buckle, okay? And so the way that we compute BPN, the capacity for an element in tension versus an element in compression, is way different. And I think it's also fair to say that for most common tension, or for most common elements, the tensile capacity is going to be usually larger than the compressive capacity. Usually elements are weaker under compression because of their tendency to buckle. Right now, since we're only talking about tensile forces, I guess you could say the term axial and tensile right now is interchangeably, but later on it won't be. So I just wanted to throw that out there for clarification. Okay. Sound good? All right. Okay. Good to go? All right. So let's see. Okay. So we're talking about design now, and we've already introduced the idea a little bit. So some of these slides I'm about to go through, I already went through last time, but I'll take some time and highlight them again just to make sure they're fresh in our heads since we're about to use them pretty soon. The star of the show is LRFD, that we are looking right now at strength limit states, and we are ensuring that our factored resistances are greater than or equal to our factored loads. And I think by now, we kind of know how to compute each of these. Before, when I first started showing these, it's like, here's this amorphous blob of an equation, but don't worry, it'll make sense. But I think now it's starting to make a little bit more sense. Right now, in terms of the resistances, we have 2 limit states that we've been addressing, gross section yielding and net section fracture. We're going to add a 3rd limit state called block shear rupture on Friday. So we'll get to that here in a bit. But right now, we're only considering these 2. Okay. So now, when we talk about design, we want to make sure that we understand what we're talking about. What does that word even mean for us? Well, when we say analysis in here, so analysis in this class has taken a little bit of a different meaning than it did last semester in 312. In 312, you know, we were summing forces and summing moments and method of joints, method of sections, shear moment diagrams, all that stuff. That's not really what we're doing here when we're using the term analysis. The term analysis is much more common, but probably it should be the term assessment, because what we're doing is we're taking an element and we're just determining what its capacity is. There is an analogous process in the land of bridges called rating, where you take an element and you rate it for vehicular loads and whatnot. That's I'm going off on a little bit of a tangent with that. Now, when we talk about design, what we're saying is, given some constraints to the problem, given some loads that we need to resist, let's select a member to safely resist those loads. And we're going to set some ground rules in this class. And we talked about this last time, that we're always going to strive to select the lightest member possible. So that's the member with either the smallest area or the smallest second number, if you will, next to the, if it's like a W12 by 49 or a W12 by 39. It's that second number, whichever one's smallest. And in this class, our problems are going to be constrained in such a way that we're all going to arrive at the same answer. If I leave the problems too open-ended, I could get 25 different answers and they'd all be right. Okay? So they are going to be constrained a little bit, but most of those constraints are going to fit within the real world anyways. As I mentioned last time, so I've got a column right here in the wall, and the architect might come in and say, you can only pick a W10 because there's no room. You know, there's no room to put anything else. And so you would only be selecting W10 sections. That is a very real world constraint, but also a very effective one in terms of ensuring that we all arrive at the same answer. So just throwing that out there. Now last time we talked about, so if we're in design mode, what we're talking about is selecting members. So we need to be able to select, or we need to be able to compute properties that'll give us some guide to look something up. So in other words, if all we were considering, like if all we were looking at is gross section yielding, let's just say that's all we were looking at is gross section yielding. We know that 0.9 FYAG has to be greater than or equal to the load, okay? And since it's pretty common to say that if I know I'm picking a W shape, I know what the steel grade is, or if I'm picking a C shape, I know what the steel grade is. So it's very possible that given a desired member, you can assign a yield strength. And so really the only unknown is the gross area. So I could solve for the gross area by just dividing both sides by 0.9 FY. So as long as I pick a member that has a gross area at least bigger than this, then I know I've satisfied gross section yielding. That one's done. What about slenderness? Well, I know that L over R should be less than or equal to 300, and I use the term should be because it doesn't have to be less than 300, although pretty much everybody's going to apply that. So if L over R needs to be less than or equal to 300, I can flip that around and say that the radius of gyration needs to be bigger than L over 300. So compute L over 300, and as long as I'm picking a member that has the smallest radius of gyration at least bigger than that, I know I'm good. So I've satisfied two limit states by just rearranging these terms and ensuring that I pick a member that it has at least properties bigger than those yellow boxes. So that part's easy. The hard part is net section fracture. Net section fracture is a little tougher to just derive an equation, right? Because there's too many unknowns to be able to just arrive at an answer. Because ultimately what we would like to be able to do is solve for a property that we can look up. And that's kind of impossible given the variability of net section fracture. Because for one, how do we compute capacity according to net section fracture? Well, we need the net area. The net area is a function of both the gross area and the plate that it's going through, either the web thickness or the flange thickness. And so since you don't know what that is starting out, you can't really solve for anything. I'll do you one better. What about the shear lag factor? Okay, shear lag factor is a function of the connection eccentricity, which is a function of the centroid. That one's even tougher. So you can't really just derive an equation for net section fracture. It doesn't really work that way. Instead, what you got to do is you got to make a guess. Okay, if you want to get to the point of just picking a member, because to be clear, what we're after in the initial stages of a design is we open the manual, and the manual has, I mean, how many different shapes are listed in here? There's There's hundreds of shapes listed in here, right? And so what we want to be able to do is take that and whittle that down to at least one answer to begin doing some math. So what we're going to do is we're going to make a design assumption. And we're going to assume that the effective net area, which is AN times U, we're going to assume that that product, that AN times U, is about 75% of the gross area. Now, by the way, you ought to just take a look at all the homeworks we've done so far, all the examples that we've done so far, and see how close this is, how good this is. It's not perfect, but it's pretty good. It's not bad, okay? So what we'll do is we'll go back to our resistance expression, and instead of net area times U, we'll put 0.75 times the gross area. So now we can take this equation, rearrange it, and get something we can look up. And so now we have a gross section, or a gross area 1 for the gross section yielding, and a gross area 2 for the net section fraction. We have these two different expressions. We're just going to take the biggest of these two. And the biggest of these two expressions, so they both have the same numerator, so the biggest of these expressions is the one that has the smallest denominator. So what I'll do is I'll just compute a big old gross area design and say it's the factored load divided by the minimum of these two quantities, and then use that for the purposes of looking up a tension member. Does that make sense? So that's going to be our essentially our process. So let's go through our process. So the first thing we're going to do is we're going to determine a factored load. So we're going to 1.2 dead plus 1.6 live, all that jazz, to get a factored load. Then what we're going to do is we're going to compute these two design parameters. So I'm going to call them design parameters. They're not actual properties of a shape in the manual. They're just tools that we're going to use to look up a shape. Okay? So we're going to compute a design gross area and a design radius of gyration. Okay? And based on these two, what we're going to do is we're going to go to the manual. We're going to take the lightest shape that we can find that can safely that meets these two design parameters. But we don't stop the problem there. It's very tempting to say, "Oop, there's the member, we're done." No, we can't do that because we have to analyze that trial shape to verify its performance. And really the big limit state that we need to assess is net section fracture. Now, it is customary to just analyze them all so that we can get efficiencies for all of our strength limit states. And so what I like to see at the very end of the problem is a summary statement, summarizing the results and computing the efficiency of the design. The reason why I think that's incredibly important is twofold. One, most software packages, if you use software to do any type of design, that's what it's going to do. It's going to spit out efficiencies or performance ratios for each limit state. But two, I want you to get into the habit of taking an element and analyzing it at the very end. Because right now we're only dealing with about three limit states. We got gross section yielding, net section fracture, and slenderness, right? It is not uncommon for a bridge girder, for example, to be looking at 20 or 30 different limit states. You know, you've got looking at the fatigue 1, fatigue 2, different strength limit state combinations. So under construction, you know, we might have strength 1, strength 4, you know, all that. So, I mean, I'm just rattling on all these different, you know, cross-section proportion limits, service 2, service 1, you know, all these different limit states that after a while, like you've made a lot of assumptions, you've gotten a girder, you should just analyze that girder and summarize what you've got at the very end. It's just good practice to ensure that the design is safe. Okay. Some final notes. Again, step 4 is a very critical process. That's the one where you're analyzing the shape. Again, you are making assumptions to get to that shape, and the main assumption is what the relationship is between effective net area and gross area. You're just guessing that. It's a good guess, but it is a guess. So you need to analyze the shape and verify its performance. And it is possible that you analyze the trial shape and it doesn't work, okay? And we may see an example of that this week. So I just want to mention that. Now, the other thing I'll mention is that in step 5, the term efficiency is mentioned, and I mentioned that before, but efficiency is basically taking the load and dividing it by the resistance. And so the idea is, a good rule of thumb is that if the efficiency is 90% or greater, you're probably doing pretty good. Now, I want to say a couple words about that. If the efficiency is 89%, that does not mean you need to redesign the member. But really what we're saying here is if you calculate an efficiency and it's 40%, you either did something wrong or you could probably pick a lighter member. Okay, just point blank. The other thing I'll say about efficiency is the equations that we're using right now are pretty linear, in how they're formatted. When we start looking at beams and columns, the equations are going to get a lot messier, okay? But the design aids that we use and the tools that we use, you'll kind of see this, especially with beams, you'll kind of see that we really are picking the lightest shape available because the design aids are sort of configured to help you do that. Well, that lightest shape might actually result in an efficiency of like 77%. That doesn't mean it's a bad design because I challenge you to find a section that's lighter, and you'll see what I mean when we get into, especially when we get into beam land and what have you. But if your value is quite low, I would evaluate the next lightest section. And the thing with efficiencies, like spinning the wheel and the Price is Right, is we want efficiencies to be as close to 100% as possible without going over. If the efficiency is over 100%, that means the loads are greater than the resistance, and that means the design is unsafe. Okay, does that make sense? So we don't want that. And again, I'm sad that I brought up the Price is Right last time, and only like a few of you even knew what I was talking about. This is just breaking my heart, man. Just saying. Y'all seen this before? I just want. Okay, all right. A couple of you say, okay, thank goodness, good. I'm not that old. Okay. All right, so we're going to look at a tension member design. We're going to look at selecting the most economical C shape of A36 steel. Okay, it is to be used as a 21-foot long tension member. The channel will be used to support service dead loads. My grammar is horrible there because I said it's just will support. I meant to say will be used to support, and I think what happened is I knew that was going to go off on another line, and I didn't edit that appropriately. The channel will support service dead loads of 100 kips of dead load and 120 kips of live load. When I say the term service load, that means it has not been factored. Okay, that's what the term service load means. And it's to be connected using 3/4 inch diameter bolts. Okay. Now, keep in mind some of the constraints. I've told you the grade of steel, and I have told you that we are picking a C shape. Okay. I've told you that we're picking a C shape. And the reason that I did that is so that we all arrive at the same answer. Okay, that's why this problem is formatted this way. And that's not, again, these constraints aren't really that unrealistic. I just want to make sure that everybody's aware of that. Okay. Come on. Okay, so let's go through a couple things before we move on. I want to start listing a couple of known quantities here before we begin, just to make sure that we're all on the same page. So let's just look at first off the material. So basically what I'm doing is I'm going to this part right here, and I'm saying it's A36 steel. What information can I glean from the fact that this is A36 steel?
Yield stress and tensile stress.
Okay. Oh, bless you. It would help if I drew with a pen, not a highlighter. And what is Fy and Fu for A36 steel? Okay. All right. So Fy is 36, Fu is 58 KSI. All right. Let's see what else. How about this? We know that it's 21 foot long. Okay. So ooh, go away. What can I do with that 21 feet? What would make sense from a math standpoint? Convert it to inches. And what is 21 times 12?
252.
Okay. All right. Let's see. Okay, and one other thing I'm going to mention are the bolts. I think it's fair to say we could just agree on that, right? That if it's a 3/4 inch diameter bolt, the whole diameter is 7/8 of an inch in diameter. Everybody good with that? Okay, I figure that part's pretty straightforward. Okay. All right. So let's go through this step by step. Okay, so what's going to be the first step regarding design? What do we need to do? What's that? Well, we're going to do, but make a guess based on what? Factored loads. We need to factor the loads. So we were given that the dead load is 100 kips and the live load is 120 kips. So therefore, if I wanted to calculate the ultimate factored load, what would it be?
1.2 dead plus 1.6.
There you go. Yeah, we don't need to look at any of the others. Oh, sorry. And again, we up that live load a little bit more because we're less certain about it. And that's not 100 kips, that's 120. Okay. So 1.2 dead plus 1.6 live. What do we get for this? Bless you.
312.
312. Do I have a second? And again, I'll probably use K and KIP interchangeably. Just bear with me on that. Okay. All right. So going to what you were saying, the design assumptions, that's essentially what we're going to be doing in this step 2, which is computing our design parameters. Okay. And so the way I like to do this, at least the first time, is we know that the expression is a big old fraction, and on the bottom of that fraction is a denominator. So let's go through that. Okay, so we've got, on the bottom, there's 2 terms. So there's 0.9 Fy. Let's go ahead and compute that. 0.9 times 36 KSI is what? 32.4. And we have 0.75 FU. Did I get that right, or I missed something? It's squared, right? Because that bottom term, we have a 0.75 squared. One of those 0.75s is the resistance factor. The other 0.75 is that design assumption, the one that the gross or the effective net area is 75% of the gross area. So this is 0.75 squared times 58 KSI. What does this come out to be?
32.62.
All right. Okay. So what we're going to do, the reason why we went ahead and did those is we're going to say, therefore, AG min is, on the bottom, we've got the minimum of 0.9 Fy and 0.75 squared Fu. And then on the top, we have our load. So which one are we going to use? We're going to use the 0.9 Fy, or we're going to use the 0.75 squared Fu? There we go. That's the one we're going to use. So this is 312 kip over 32.4 KSI. And what do we get for this?
9.63.
9.63 what?
Oh, 9.629.
No.
Inches square.
I'm saying, yeah, the units are square inches. No, but you're right. Now, I'll say this. Let's talk about that. I wouldn't go any further than 3 decimal places. There's no real sense to do that because the manual doesn't list the properties any more detailed than that. So there's no real point in going past that. But the units are square inches. Okay. So now, do we have another design parameter that we can compute? We can use, exactly right. We can compute our radius of gyration for design. So this is, what was that? What was the length? 252 inches? Which is what? .84 inches, right? So this is where converting that to inches, that's where that's valuable. Because if we left this as 21 over 300, like that would be the right answer, but it would be whatever that is in feet. And then when we go to the manual, none of the radii of gyration are in feet. They're all in inches, which is why just go ahead and convert it to inches and whatnot. In fact, whenever you're looking at capacity calculations, it's usually a good idea to go ahead and convert the length to inches. We're going to see some slenderness quantities show up later with columns and beams, and it kind of just makes sense to go ahead and do that. So, okay. So now what are we going to do? Okay. So step 3. Step 3, we're going to choose a trial shape. Now, we have 3 constraints. Okay. What are our 3 constraints? Well, the first, the gross area needs to be greater than or equal, I can do better than that, greater than or equal to 9.63. The minimum radius of gyration needs to be greater than or equal to 0.84 inches. But what's the other constraint? It's an obvious one. It's got to be a channel, right? We're limited to C shapes. So, with these 3 constraints, now what I want everybody to do is open up that little gold book that I know everybody brought with them today. Because everybody brought it with them because it's steel design. Everybody brought it with them. They have